A ripple counter is sometimes referred to as an asynchronous counter, but I don't love that phrase as it seems to imply that there's no clock signal. There is. What distinguishes a ripple counter from a synchronous counter is that the clock signal is not shared between all of the flip-flops in a ripple counter. A ripple counter also relies on a falling edge clock signal. If you're using a flip-flop chip with a rising edge trigger, you may need to use inverters to implement this. A ripple counter is also designed in a vastly different manner than a synchronous counter. While all counters can be described with a state diagram, a ripple counter does not use a transition table. The design of a ripple counter is as follows. Step 1. Wire up the flip-flop input so that it toggles on each clock tick. For a T flip-flop, the inputs will connect directly to VCC. This is similar for a JK flip-flop, where both J and K connect to VCC. For a D flip-flop, if we want the output value to toggle, we want the next output, and therefore the input, to be the opposite value of the current output. So connect the input to the prime of the output. Step 2. Ripple the clock. The clock source itself connects directly to the least significant bit flip-flop. Connect the LSB output to the next flip-flop clock. Then that output goes to the next flip-flop clock, and so on. If the subsequent flip-flops don't have falling edge clocks, connect the primes of the output to the clock inputs. Step 3. Determine what the asynchronous pins will connect to. We'll consider that situation in detail for the specific examples we do in this video. Before getting to specific examples, I need to point out that a ripple counter cannot be designed to count out of sequence. That can only be accomplished with a synchronous counter. Let's start by designing a 3-bit ripple counter that counts up. Let's do this with JK flip-flops. Connect all of the inputs so that they toggle. Then ripple the clocks. The LSB gets the direct connection to the clock signal. Then the LSB output goes to the next flip-flop clock. Then that output goes to the MSB flip-flop clock. For this particular circuit, as we have no need to asynchronously preset or clear any of the flip-flops, we can deassert those pins. We can analyze a timing diagram to see how this works. Let's assume that all of the flip-flops initialize with a value of 0. On the first falling edge of the clock, the LSB flip-flop, C, will toggle. Then it toggles again on each subsequent falling edge. Toggle, 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 and so on. The LSB signal can be used to determine when the next flip-flop toggles. When C has a falling edge, flip-flop B will toggle, and so on. Then, flip-flop B will cause the MSB flip-flop, flip-flop A, to toggle when it has a falling edge, and so on. So, if we look at the values on each flip-flop at each time increment, it starts at 0, becomes 1, 2, 3, and so on until it reaches 7, in which case it resets back to 0 again. A cool thing about this is that if we look at the complements of each output, we see that while the Q values count up, the Q prime values count down. So this counts both up and down simultaneously. While the same thing happens with a synchronous counter can be designed specifically to count down, which is not necessarily true for a ripple counter. This same process can be expanded upon to create a 4-bit counter or a 5-bit counter and so on. It's relatively easy to design, but has some drawbacks. Remember how a ripple carry adder has the issue of increasing delay as more stages are introduced into the circuit? We can't rely on the last output to be valid until the signal has propagated through each of the previous stages. The same issue holds for a ripple counter. As more stages are introduced, the more lag there is between the first and last stage. In fact, the issue is worse because it's a sequential circuit and not a combinational circuit. There will be some lag between each and every stage. When the clock ticks, the counter value doesn't immediately increment. It takes each stage a gate delay to cause each individual flip-flop to toggle. If the number of stages is large enough, or if the propagation delay in each flip-flop is large enough, the circuit may encounter significant synchronization issues. In this example timing diagram, which is admittedly extreme to prove this point, the clock has a period of 100 nanoseconds, and the propagation delay of each flip-flop is 20 nanoseconds. While the counter does count up, there are glitches after each flip-flop output has a falling edge. It's important to point out that all ripple counters experience glitches due to propagation delay. It's just that we cannot see them with our eyes in circuits that we build. If we're simply building something like a clock, this may not be a big deal. The glitch exists, but it doesn't affect the user's experience with the product. However, if glitches could cause an undesirable signal in subsequent electronics, then ripple counters should not be used. If glitches would cause issues in a circuit, then synchronous counters should be used instead. A decade ripple counter is simply a decade counter generated by using a ripple counter. Remember, no transition table needed. A decade counter requires 4 bits, so 4 flip-flops are needed. Let's do this with the T flip-flop. Start by connecting the input so the flip-flop toggles, then ripple the clock. As is, this counter is a 4-bit counter and will count from 0 to 15 and back again. How do we get it to stop at 9? When designing a ripple counter that counts from 0 to a number that isn't 2 to the n minus 1, we can utilize a momentary glitch in the output to achieve our desired result. As soon as the output reaches the next value, 10, in binary 1010, we want to asynchronously trigger a reset and get the counter back into state 0. Consider that values of 0 through 9 will not generate resets. A value of 10 will generate a reset, and we should never see outputs greater than 10. Asynchronous clear pins tend to be active low, so a reset is indicated by 0. If we put this into a K-map, we get a minimum POS expression of A prime plus C prime, or the quantity of A, C prime, which we can use a NAND gate to build. I can build this circuit and show it off, and while we can't see the value 1010 ever occurring on the output, it does occur for a brief instant in time, as long as it takes for the propagation delay of the NAND gate, in addition to the amount of time it takes the asynchronous clear pins on the flip-flop chip to clear the outputs to each flip-flop. Based on the datasheets for the 74112 JK flip-flop and 7400 NAND gate, the total time that the counter is in the 10 state is going to be somewhere between 20 and 30 nanoseconds. Just because we can't see this glitch doesn't mean that it isn't fast enough to trigger an undesired result if it's connected as an input to another digital logic device or a microcontroller. If a glitch could possibly screw up circuitry further down the line, then a ripple counter is not the circuit that should be designed. If glitches could be problematic, then synchronous counters must be used. Just as it's possible to have a ripple counter count from 0 to a value that isn't 2 to the n minus 1, it's also possible for a ripple counter to count back to a value that isn't 0 once it has cycled through. This can be achieved by using both the asynchronous preset and clear pins. Consider this state diagram as shown on the screen. This counter will go through the sequence 2, 3, 4, and 5 repeatedly. How many flip-flops do we need to build this? 3, because the largest value in the count is 5. Let's use a JK flip-flop. Connect the inputs so they toggle. Ripple the clock. This is always the procedure. No transition table needed. Then consider the glitch state. That will be one after our last desired state. We want to see 5, so 6 will be the glitch state and should trigger an active low reset. 7 is a don't care. Put these values into a K-map and we see that our reset logic will be the quantity of AB prime. We don't want to connect that to the clear pins on all of the flip-flops, because we don't want it to reset to 0 again. We want flip-flop A, the MSB, to be 0, B to be 1, and C, the LSB, to be 0 to generate the value 010, which is 2. That means AB, quantity primed, connects to the clear pins on A and C and the preset pin on B. The other unused asynchronous pins should be deasserted. When I demonstrate the circuit, you can see it repeat the cycle from 2 through 5. Remember, there is a glitch to 6, even if we can't see it with our eyes. When designing a circuit that resets to a value that isn't 0, consider the value required on each flip-flop to generate that reset value, and then use asynchronous preset and clear pins accordingly.